Welcome to the exercises for Chapter 4. The first couple of exercises are entirely focused on the Gaussian function. It's a super important function in basically everywhere in math, statistics, physics, signal processing, you name it. If there's math involved, the Gaussian function is probably involved somewhere. So anyway, we are going to start with this exercise, exercise 1, with implementing the basic Gaussian formula in Python code. I will show you that equation in a moment. And here I give a recommendation, which is to break up one equation into 3 separate lines of code. This is just a bit of a tip for translating mathematical formulas into code. I will explain more what I mean by this when I show you this equation in a moment. So implement that equation in Python, set the sigma parameter to be 0.73, and then that's going to produce this plot over here. You can see the x-axis values go from -3 to +3. Okay, so then we want to create this panel here, and this shows a bunch of different Gaussians. So I used 50 different Gaussians. Where is that here? 50 Gaussians with sigma ranging from 0.1 up to 3. So you can see I'm also not showing the legend of all 50 lines, so I just pick, it might be every third or fourth Gaussian to show the legend of. Now, notice that we're not changing anything else about this Gaussian. So the formula is the same. The x-axis grid for evaluating the function is the same. We're only changing this one parameter, and you can see what kind of an effect it has. So it has an effect both on the width, that is like the steepness with which the function decays, negative and positive, and it also actually affects the peak. And that's something that I'm going to discuss in more detail in the next exercise, in the next video. So this is one representation. We see all the Gaussians as lines. And then what you can do is, if you put all these different Gaussians into a matrix, then you can create an image of that matrix. And that looks like this. Looks pretty neat. It looks like shining a flashlight through the fog or something like that, like the light is fanning out here. Actually, what's going on here is that each row in this matrix here, in this image, corresponds to one of the Gaussians. And the luminance, or the color intensity, the pixel value, corresponds to the height here on this plot. So you can see that when sigma is smaller, so smaller values of sigma, have a narrower Gaussian that has a sharper peak. And then we get out here, the sigma parameter gets larger, and you can see that the Gaussian is now, some of these lines actually even just look like a straight line. You can barely see the Gaussian curve. And that is going to be relevant for the next exercise. But anyway, the point is that you can see that they are much more gradual, so the color is much more towards black here. Okay, so that is the exercise here. Let me now scroll up and show you the Gaussian formula. So here is the formula for the Gaussian. So we have 1 over sigma times square root of 2 pi times e to the, and then all of this stuff here, this fraction here is all inside the power. It's inside the exponent of this term e here, natural exponential. So minus x squared over 2 sigma squared. This sigma here and this sigma here are the same. And yeah, this is the key parameter that we want to modify in this analysis. Now, this is one mathematical function, but when you are implementing math functions in Python or any other coding language, it is often useful to make your code more readable, to make it less prone to errors, make it easier to adapt and parameterize and so on. It is better to implement this in, or split this up into multiple lines of code. So you can do, for example, put this term here, which is actually just a amplitude scalar term. You can put this term into one line of code, set this to be one variable. You can set this, so minus x squared over 2 sigma squared, to be another term. And then, separate line of code. And then in a third line of code, you can put these 3 terms together. So we have this normalization term, the power term, and then the e to the, and on all of that stuff. So basically taking something that's kind of complicated and splitting it up into multiple lines of code. Okay, so now I will switch to Python and walk through my solution. Here is the x-axis grid. I didn't specify how many points between -3 and +3 to use. I think 101 looks pretty good. It's kind of arbitrary. There's no real reason to use 101 versus 111 or like 113. Any of those are fine. But there is something interesting that happens with odd numbers. So there is a motivation for using odd numbers, and that is when you go from minus something to plus that same magnitude number, so -3 to +3, -7 to +7. If you're using linearly spaced numbers, if you have an odd number of numbers, an odd number of steps, and you're going to get exactly 0 in the middle. And that can be convenient for various reasons. For one thing, if it's a symmetric function that has a peak at 0, or if something interesting is happening at x equals 0, then with this function, with this setup, you will get that function value at exactly x equals 0. If you would do this, for example, here with an even number of points between -3 and +3, you're not going to get exactly 0. It's going to be, minus 0.001, and then the next value will be plus 0.001. So you don't get exact 0 in here. Sometimes that's relevant, sometimes it's not relevant, but I'll just point that out. Okay, here I'm soft coding this variable sigma. Here you can see the 3 lines of code that I'm using to implement that one math function. So this is the amplitude scalar term or normalization term. Here we have, I call this the E term. This is the term that goes inside the superscript of when it's written out in code. So minus x squared over 2 sigma squared. And then here I put them all together into the Gauss formula. So A times e to the, and then this variable. I think you agree, I hope you agree that writing it out here, although it's more lines of code, it's actually easier to read, so it's overall better. And this is just to make my point super clear. I mean, you could put all of this stuff into one line of code, and this is correct. There's nothing wrong with this. There is something wrong with this. Now there's nothing wrong with this line of code, but it's just really long and dense and hard to read. Okay, so let's set this back. I think it was like this. Okay, so there we go. This is the first part that creates the first panel. And let's see, now I create a family of Gaussians. So this is pretty straightforward. I just took all of that code and put it into a for loop where I'm looping over various values of sigma from 0.1 to 3. Okay, and then you can see I'm putting these all into a matrix that just is a convenient way to store these data. Okay, here, you can see I'm visualizing. Let's see, n is not defined, really? Oh, okay, I showed you this code, but I didn't actually run it. So let's see now. Okay, so this is just selecting a certain number of Gaussians to use. You can see I'm just skipping over by 8. That's an arbitrary number. I just thought it looked good like this. Okay, so that's the middle plot. And then here we have the matrix. So again, this is matrix G that I put all of these Gaussians into. And this is pretty straightforward matplotlib image visualization stuff. So I'm specifying the extent parameter that is defining the labels for the x-axis and the y-axis. And I set this to be gray and have these particular color values. This is the video for exercise 2 of chapter 4. But I want to start by showing one of the results from the previous exercise, from exercise 1. There, you'll remember, we created a bunch of Gaussians that were defined by the same formula, the same x-axis grid, and so on, just a different value of sigma, or this width parameter or shape parameter. And one thing we saw here is that the peaks have a very different height, right? So the value of the function at x equals 0 is very different for all of these different parameter values. And the question is, why is that the case? I would like you to think about the answer, see if you can come up with the answer. And if you're struggling or if you have some idea but you're not really sure, it's totally fine because I will now tell you. Well, actually, first we'll investigate this a little bit more, and then I will tell you. So to start with, we're going to compute the sum over all the data values for each Gaussian. Okay, and that is where we begin with this exercise, exercise 2. So remember, we have this matrix G. If you don't have this matrix, then go back to the previous exercise and just run that code. So we want to compute the sum over all of the individual Gaussians. And you can see that they start off being 18.3. What a weird number is that? And then they get smaller and smaller. So what is going on here? So what's happening here is we are actually just computing the sum over all of these values. And you can see that, well, they get pretty big, right? Some of these at the peak. For the smallest value of sigma, it's even above 1. So we're summing up all of these numbers here. And what does it mean that we have this number 18.3? Where's that number come from? Well, to get a little bit more insight into this, we don't want to compute the sum. We actually want to compute the discrete integral. So if we were doing this just with math and like a math textbook or a math course, then we would really be interested in integrating over the Gaussian. And what you would find is that the integral of a Gaussian is 1. So the integral is 1, but the sum is not the same thing as the integral. Instead, when computing the integral, we have to scale by dx, which is the width of the x-axis spacing. So that's what I do here in the code. I forgot to run this, but this is also not very helpful. This is just so you can see that, the mean is also, it doesn't give very sensible results here. Okay, so we want to sum just like we do up here, but now we're going to scale by the discrete derivative of x. Let me go back here just to make sure this is super clear. So these are drawn as lines, but these are not really lines. Actually, let me redraw this. I'm going to redraw using dots like this. Let's see if this helps us a little bit. Okay, so there isn't really a line between here because we're not computing all possible values of x. Instead, we are discretizing x. So we have this point and we have this point. So the integral over this function is the sum of all these values, but it has to be scaled by the width of the bar. You can think of like a Riemann sum if you've taken a first semester calculus course, or you can think of just the area between this bar. Here, it goes down to x equals, or y equals 0. So it's the height, and we get the height by summing, but then we also need to scale by the width, which is the distance between each successive point in the x-axis. Okay, and so that is what I do here. And now we see something interesting. So it's 1 for these first couple of Gaussians. And now the later Gaussians, basically when sigma parameter is getting larger and larger, the Gaussian is getting wider, and the numbers start to go down. They're getting smaller. So this seems really weird, right? So the question is, why is this happening? This kind of makes sense. From the theory, we know that the Gaussians should integrate to 1. Why aren't these Gaussians integrating to 1? So the answer to that question, to get insight into that, we can scroll back up here and appreciate that Gaussians should also taper to 0. And you can see that for the first couple of Gaussians, they really are going to, it's not exactly 0 because it's e to the something, which is a non-negative, positive valued only function. But it gets really, really, really close to 0. And you can see that here. But these other Gaussians with a larger sigma parameter, in theory, they go to 0, but just not in this plot. So we're actually just losing a lot of information here. So to appreciate this better, what I'm going to do is scroll all the way back up here to the beginning of exercise 1. And instead of going from -3 to +3, let's go -6 to +6. Now, that doesn't change the function. We're not changing the sigma parameter. All we're doing is changing the x-axis limits. So let's see, recreate this matrix of Gaussians. And now here you can see, so this is like around 0.1 is the largest value, or the smallest value at the boundaries. And now here with 6, so it's still for, these large values of sigma, we're still not getting all the way down to 0, but it's certainly a lot closer to 0. And that means that when I run this code here for exercise 2, this will be, again, these are not all the same, but they are, they stay up quite a bit longer. Okay, so now let's have a look at the discrete integral. These are not all going to be 1s, but you can see these stay much, much larger than they did before. Okay, so how much do we actually need to do here? Well, in theory, the integral of a Gaussian should go from -infinity to +infinity. So yeah, I mean, how much do you want to get into this? You can have this go from minus 10 to the 32 to plus 10 to the 32, but that's really not necessary. I think one of the important things I want to highlight here in this video is that you have to think carefully when you are translating concepts in mathematics into code, especially with applied math, areas of applied math like statistics. So it's not really that important that the integral doesn't get to exactly 1. It's pretty close, and we understand why. Now, this is not just some weird academic thing. This really comes up in probability functions you will see when we talk about PDFs and CDFs and computing p-values. This has real practical implications for the kinds of probability values that you can get. So it is something to be aware of. Okay, and then there's one more thing I want to show you in this video, and that is, actually, let me also get rid of these dots here. And that is removing this A term here. So I'm going to literally just cut this out. Rerun the Gaussian, and maybe I'll set this back to go from 3 to 3, minus 3 to plus 3, rerun the Gaussians, and replot here. Okay, so now you see that the Gaussians all peak at exactly 1. So they all have exactly the same peak. They don't all okay, maybe I changed my mind. I do want this to be a little bit of a broader x-axis range. Let's see here. Okay, this is good. So now we see different Gaussians. The overall shape is the same, but now they all peak at exactly 1 because I've removed this amplitude modulating factor from the results, okay, or from the equation. So we can see this also looks different. And now this is what I want to show you. When we compute the discrete integral, we see it still should be close to 1 for some, there's going to be one Gaussian where the value of A, this scaling parameter, just happens to match. So we get an integral that's close to 1. But now you can see the integral is very different, and it's very different for each Gaussian. So these are just trade-offs. There are going to be situations where you actually do want all the Gaussians to have a peak of 1 at x equals 0. Normalization is a tricky thing in statistics and data science and signal processing, so it's useful to understand the implications and also implementation of different ways of normalizing functions. Welcome to the third exercise of Chapter 4. The goal of this exercise is to implement a few of the basic and foundational descriptive statistics in Python without using any libraries like NumPy or SciPy. So you're only allowed to use any functions that come with a base install of Python, so nothing that you have to import. And why would you do this? Well, you do these kinds of things basically just as an educational experience to make sure that you really understand how to compute the mean and the median and the standard deviation. Okay, so that is the point. We start with this little data set here of integers, a lot of 7s for no particular reason that I'm aware of. Maybe I thought really is every other number is, oh, I see the pattern. Okay. It's 1, 2, 3, 4, 5, 6. And then there's 7s in between. So I don't know why I come up with these sequences sometimes. Okay, anyway, here's the point. You want to write a Python function that will take a list as an input. Now, this should be a regular Python list, not a NumPy array, again, because we're not using NumPy for this first part of the exercise. So a function that imports a list and then computes the mean, the median, and the variance of that list. And then you can print out your results so these are my results from my function. And then just for confirmation, to make sure you're getting the correct result, you can also print out NumPy's results. And of course, your results should match with the results of NumPy. Okay, so then there's more text that I have in here, but I'm going to first switch to Python and show you my code solution, and then I'll get back and talk about some of this stuff. So here is my Python function. I call this function compute stats. It inputs a variable that I here called data, and here's the number of elements in data, and the mean is very simple. We just sum and then divide by n. The median, to compute the median, first you need to sort all of the data, and then you need to take the either the middle value, if it's an odd number, or you compute the average of the two middle values if it's an even number of elements. So sort the data, and then here I say if the length of data is odd, so this percent sign here is the modulus. So if the remainder of the data length after dividing by 2 is 1, that means it's an odd number, n is an odd number, then we just take the middle value here. And, well, this gives us an integer, and here I'm just showing you that these two are equivalent. So mathematically, you would write down n plus 1 divided by 2. This is the math way of notating the index. In Python, you can notate that using n divided by 2. This will make sure that we get an integer answer here. Okay, and then if it's even, so if n is an even number, then we actually have to take n / 2 minus 1 and then n / 2. So here I sum those values and then divide by 2. So basically it's just because if there is no exact center value, you take the average of the two centermost values. That's how you compute the median. Okay, so then finally we have the variance, and here I do this using list comprehension embedded inside a sum and then a division. So we take the each data point, so I say for I in data, so we're looping over all the elements in the list, and then we subtract the mean, so we're mean centering, and then squaring, and then sum up all of those values and divide by n minus 1. That is the formula for the variance. And of course, to get the standard deviation, you would just take the square root of that. So pretty straightforward, but again, it's a good educational experience to write out all of these equations, all of these algorithms by hand like this. And then, okay, so now I'm going to run that. Here is the vector that I specified in the book. I'll get to this line later. And let's see, so here I call this function. And now I'm comparing this to NumPy's mean, NumPy's median, and NumPy's variance. Actually, let me get rid of that parameter. So numpy.var for variance, and then compute the data. Pretty straightforward. All these things should be equal. This is just some, hacky looking code to print out that table that I showed in the book. Okay, so let's see. The means match perfectly. The medians match perfectly. The variance, it's like sort of kind of close, but not exactly. So that's how we get back to this text. Perhaps you reproduced the results exactly for mean and median, but not for variance. Okay, so what's the deal with that? The deal with that is the parameter in NumPy's var function and also the std function, the standard deviation function. The parameter is called DDoF or DDoF. And I don't know how the developers wanted us to pronounce this, but it stands for the denominator degrees of freedom. And it actually tells us what to subtract from n, from the sample size, when computing the variance or the standard deviation. Now, from the statistics theory, we know that it should be n minus 1 for a sample variance or n for a population variance. However, the default parameter in numpy.var is actually 0. So that's going to compute the population variance, not the sample variance. So to compute a sample variance and also a sample standard deviation, you actually need to specify this optional additional input. And that is the line that I cut out here. So we can put that back in. So you can see numpy.var data, that's the input, and then DDoF or DDoF. Maybe the first D is silent, so you just say dof. Anyway, okay, so now let's see, I'm going to print this out again. So here was where there was a discrepancy. And here there is no discrepancy. Okay, so that's very good. And then, I think it's nice to use random numbers just to make sure that you're really getting an accurate solution and there's not just some quirk about this particular set of numbers. That's the reason why I asked you to generate a new random data set. So each time you run this, you should be able to get exactly the same results as the outputs of these NumPy functions. And then, there's no particular reason for me to specify using random integers between 4 and 20 and with a sample size of 24. That's, sometimes I put these little additional things into the exercises just to give you more practice with different ways of generating random numbers or simulating data like this. Okay, so let's run this once more. And then, yeah, we see again, these numbers match exactly. Okay, so one final thing I want to mention in this video is, why would you go through all this stuff? Isn't it crazy to write out all this code just to compute the median when, you can just use numpy.median? Obviously, the answer is yes, you should always use numpy.median. The only reason why you would write this out here is only in this context, in an educational context, in a course, in a book, because it's important that you understand how the median is computed and not that you think it's just some weird, complicated, magical formula that only a PhD in mathematical statistics can understand. No, 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 it's not like that. Median is super simple. So you do this once, you understand how it works, and then in the future, once you understand it, you use this. Now, that said, there are exceptions. There are other cases that I will go through later in this book where I believe that using functions provided by Python libraries is tedious, it's pointless, it takes too long, and it's going to be much faster to understand the math of the statistics and to implement the code yourself. So we'll get to those examples later in the book. This is the video for exercise 4 of chapter 4, and this exercise follows directly from one of the quirks that we discovered in numpy.var in the previous exercise. In particular, we saw that the denominator degrees of freedom parameter defaults to the population variance, and you need to specify that DDoF parameter equals 1 to get a sample variance. Now, here's the question that we are going to explore in this video, in this exercise. Does that parameter really matter? Does it matter if you specify the denominator as n or n minus 1? And now here I say intuitively, you should have the idea, the understanding that when n is small, it makes a big difference. When n is big, it doesn't make a big difference. So the difference between 4 and 5 is big, right? That's like a 20% difference. The difference between 999 and 1,000 is small, even though it's numerically, it's still, both of these are just one number, one integer off from each other. Okay, so we're going to run an experiment. Here's what you do. Generate random integers between minus 100 and plus 100. Compute the variances on the same data sets with this DDoF parameter being 0 and being 1, and compute their difference. So we want to know empirically, does the estimate of the variance really make a difference according to setting this denominator degrees of freedom parameter? Now, because this is a random experiment with random numbers, we want to repeat this multiple times. So for each of these different sample sizes, and let's see, the sample sizes range from 5, so sample size of 5 to a sample size of 100. And then you repeat each of those experiment repetitions 25 times. And what you see here is these error bars in which the dot corresponds to the average of the variance difference between the DDoF parameter being 0 and the DDoF parameter being 1. And the error bars here are the standard deviations across the 25 experiments. So what you see, well, actually, I'll show you the Python code first, and then we'll talk about how to interpret this plot and what it means. So here are the parameters for the experiment. We have sample sizes ranging from 5 to 100 and 25 repetitions of each random draw of numbers for each of these sample sizes. Okay, and then here you can see I'm going to put all of the results into a big matrix, which I'm initializing as a zeros matrix. We need results for each of the 25 repetitions for each of the sample sizes. Okay, so then we have a double for loop over here. And an interesting question for you is whether you really need both of these for loops, or whether it's possible to run this experiment and do this exercise with only one for loop. That's a little bit of a challenge, and I'm not going to tell you the answer, well, the answer, no, I won't tell you the answer. But it's something to explore. That has nothing to do with statistics, by the way. If you want to see if you can figure that out, that's just something about Python coding. Okay, but anyway, I have this coded here as a double for loop. So we generate some random data between minus 100 and plus 100 using the specified sample size. And then let's see. So here we are computing the variance twice. Same data, right? So the variance is the same. We're just changing whether we are dividing by n or n minus 1 over here. So ignore these lines over here. This is for exercise 5 for the next exercise, the next video. And so here, yeah, we're just storing these the variance differences in this matrix here. Okay, so run this code. That should take, yeah, okay, that takes less than a second to run. Then I get the, actually, maybe I will, let's just check the size of this. So d.impact.shape. And you can see it is 96 by 25. So 96 corresponds to all of the different sample sizes between 25, between 5 and 100 inclusive, and then 25 repetitions. So here I take the average and the standard deviation across axis 1, which is all of the experiments. So that means that this is going to be a vector of 96 average differences of the variances. Okay, and then the standard deviation. Now, the rest of the code in this cell is pretty straightforward. I'm just making an error bar. So what does this mean? How do we interpret this? So a couple of things you see. One is that as the sample size increases, the difference between DDOF equals 0 and DDOF equals 1 decreases. Now, again, this is exactly what we should expect. The difference between 5 and 6, or 4 and 5, is much bigger than the difference in a denominator, and a fraction is much bigger than the difference between 99 and 100. So that's a pretty sensible result. You can see also that not only is the average variance decreasing, but the standard deviation is also decreasing. So again, the larger the sample size, the less it matters whether you divide by n or n minus 1. You can also see that the variances here are big, right? I mean, 400 to 1,000 here for the smallest sample size. That's a range of 600. That's really big, right? So what does that mean? How do we interpret that? Well, the thing about variance is that it is dependent on the numerical values in the data. So as we scale the data, this number is going to scale as well. So 400 to 1,000. So that's a range. Let's just call that 600 units, just to have a ballpark figure to compare against. So what I'm going to do now is repeat this. I'm just going to divide this by 10, right? So literally nothing in the experiment is changing except the data are being scaled down by a factor of 10. Okay, so then we can run this again. And now we see that here, this is a range of 6 instead of being 600. So not surprising, we scaled down the data by 10. This scaled down by 100, but that's because variance is a squared measure. So the point that I wanted to make here is that the magnitude of the variance itself is not really interpretable because it's in the scale of the data. Or I shouldn't say it's not interpretable. That's not correct. But measures in statistics that are non-normalized, that are based on the units of the data without any normalization, can be difficult to evaluate and interpret on their own and compare across different data sets. That's one of the messages I wanted to get at here. Exercise 5 of Chapter 4 follows directly from the previous exercise. So you really need to have gone through the previous exercise in order for this one to make any sense. Now, one of the things I discussed at the end of the previous video, which I also mentioned here in the text in the book, is that it can be difficult to evaluate the numerical quantities of statistical results like variances without any normalization, and that's because these results are scale dependent. So remember in the previous video, I closed the video by dividing the data by 10, and we saw that the variance numerically reduced by a factor of 100. What we're going to do here in this exercise is recompute the variance difference, but applying a normalization. So in the previous exercise, we basically just computed the numerator here. So it was S1 minus S0. And actually, looking at this now, it's got S. I think we're going to change this to V because it's the variance that we're computing, not the standard deviation. Anyway, so when you see this in the book, this will say V1 minus V0, and the 1 and the 0 correspond to the denominator degrees of freedom parameter setting. So what we are going to do here is normalize this difference according to their sum. So taking the difference between two values and dividing by the sum of the two values is a fairly common normalization procedure in data science. So you'll see things like this happen more often when you work in statistics and machine learning and data science and so on. Okay, so let's see. And then, yeah, basically just redo the previous exercise with this normalization. There's more to say here, but I'm going to show you the code in Python and then discuss the plot and how to interpret it. So you don't actually need to write an entire set of new code for exercise 5. Instead, you just go back to the code from exercise 4, and all you need to do is basically just recompute this var diff variable here. So you can see, you can comment this out if you want, but it doesn't matter because it's going to get overwritten. So here I have the difference, which is exactly the same as what we computed in the previous exercise, the previous video. And then I have this called A, and then here is the sum of these two variance differences. And then, yeah, this is, it's just that simple. Okay, so let's see, redo this. Don't need that. And let's see, then we recompute this plot here. Now, remember, there was error bars before. Here, there's still technically error bars, right? But the error bars, they're tiny. Maybe they're so small that, it's just hard to see. Let's see what these numbers actually look like. So d-doff impact, we can just dump out all these numbers and, this is kind of funny. So it appears to be exactly the same number, not like really kind of close, but literally exactly the same. Now, maybe, okay, so I was still dividing by 10. I don't know, maybe I should have gotten rid of that. They're exactly the same. So we've gotten rid of the scaling problem. That was the reason why we did this normalization. But why are they exactly identical for every single repetition? It's really, it kind of doesn't make sense. Maybe you think that there's a mistake in the code somewhere, but we know that, we do get, let me uncomment this and comment out these lines. So when we, from the previous exercise, we still do get quite different numbers each time we rerun the experiment. So there isn't anything wrong with the code. And in fact, there's nothing wrong at all. It's just a little confusing. And let's see. So the error bars are actually exactly 0. I'm going to talk about that in a moment. First, I want to just point out the variance difference. Here, now this is in proportion. So you can see that for these small sample sizes, the variance estimate will differ by, 11% or whatever this number is, a little over 10% for a small sample size of 5, according to the d-doff parameter, whether you set it to be 0 or 1. And you can see that this gets pretty small. So here with a sample size of 100, this the difference in variance is whatever that number is. It looks like a little bit under 1%, something like that. Okay, but let's get back to this issue of why the error bars are so small. In fact, the standard deviation is 0. So it turns out that the impact of the degrees of freedom on the scaled variance is this expression here, 1 over 2n minus 1. You can see that there's no data in this expression. And what do I mean by this? What I mean by this is that this expression here, which is two variance terms, the difference of two variance terms divided by the sum of the variance terms, these are based on data. But I claim that reduces to one, this expression here with the divisive normalization reduces to this expression, which has nothing whatsoever to do with data. And that's why it's independent of the data. So every time you rerun this experiment using different numbers with different randomly selected numbers, you're always going to get exactly the same proportional difference because this fraction ends up working out to being based on n and totally independent of the data. And I don't go through the proof of that, but it's basically just a little bit of algebra. Here we have the equation for variance. This is equation 4.5 in the book. And yeah, if you basically just plug this in, you do some algebra, and you will find that all these x terms, this summation term, starts to cancel, and you're just left with some n terms in the denominator, and that's just how it shakes out. So then here we get to the final conclusion, the grand conclusion from this exercise and the previous exercise, and it is this: getting the denominator degrees of freedom parameter wrong is not going to crash the universe. It's not going to be a huge deal. It's going to be a difference in a couple of percentage points of variance. That said, of course, you should do the correct thing whenever possible, but don't lose sleep over something like the DDoF parameter in numpy.var and numpy.standard deviation. The goal of exercise 6 in chapter 4 is to explore the impact of outliers on the mean and the median in data and how that is related to the sample size of the data. Now, I hope you have the intuition that the larger the sample size, the less impactful an outlier is, particularly on the mean. And, well, I mean, I think that should be intuitive because the more numbers you're adding together or averaging together, then one individual weirdo is not necessarily going to screw up the whole batch of numbers. Okay, so to test this, you want to create a data set of 50 numbers drawn from a standard normal distribution, compute the mean and the median of that distribution. Now, we expect that the mean is 0 and the median is also 0, but these are the theoretical, like, population parameters in an individual sample, especially with a relatively small sample size. That's not, the mean and median are not trivially going to be 0. They're trivially going to be somewhere in the neighborhood of 0. Okay, so let's see. And then, plot create a histogram of the data set and plot the mean and the median. You can see they're close to each other, but they are different from 0. And then you add an outlier. And to create the outlier, you take the largest value of the data and replace that largest value with itself to the 4th power. So you identify x max and you replace it with the same value raised to the 4th power. So we're just taking one big data point and making it really, really big. Okay, and then, so then you can create these two graphs and then repeat that for exactly the same code, just change the sample size from 50 to 5,000. And I'm going to talk more about interpreting these graphs and what we can infer from them in a moment when I switch to Python and produce these graphs in code. Then the last thing to do is to print out the numbers. So with the sample size of 50, the mean increased. So this is the change in the mean due to the outlier. So you compute the mean with the outlier and without the outlier. And with the outlier, the mean increased by 0.62. Again, that is, that's just for this particular data set. So it's going to be a random number, of course, because these are random data. And for the bigger sample, the mean increased by 0.03. So it was really, like an order of magnitude difference here. And then the median increased by 0.00. Again, I will interpret this in a moment in the Python code. Okay, so some observations I have in text here, but I'm going to explain that in context of looking at the code. So here we have the code for exercise 6. I specify the two sample sizes. It's soft-coded here so that you can play around with this. You can try what happens when the sample size is 5, for example. That's a pretty small sample size. But, there's plenty of studies, especially like clinical studies or some kind of neuroscience studies also sometimes have these tiny, tiny sample sizes. Okay, so let's see. Here I create data, and then here I create the outlier by finding the largest value in the data, and then I replace that value by itself times or to the power of either 1, which means itself, or to the power of 4. This is just a little bit of tricky, like kind of hacky looking code to get this to work inside of this this for loop here over the including an outlier or not having an outlier in there at all. Okay, so then we compute the mean and the median, and then I create a histogram and plot the means and medians on top of each other. So let's see what this figure looks like. Here we have a bunch of histograms, going to be 4 histograms. This one looks like it's bimodally distributed, maybe because there's a notch. Here, there's some data missing here. I'm going to talk about that a little bit later. But let's see. So here is without the outlier and with the outlier. And you see the distributions are almost the same. They're not identical because the way that the histogram boundaries get cut up depends on the data itself. So when the data change, it's possible that the histograms will change, but they won't change that much, of course. Okay, but you do see that the mean and median are really, really similar to each other here, much more different from each other here, but you don't see that same effect here. So here it looks like, so with the large sample size, looks like the mean and median are identical. They're probably not exactly identical, but I think they are very, very close to each other. Here, they're still quite close to each other, but sort of visibly, noticeably separated. Versus here, they were, really, that's a visually noticeable effect. Okay, so now let's print this out. We see that the mean was impacted by the presence of a single outlier by half of a unit, half an integer, which these are all standard deviation units, right? Because this is numbers drawn from a standard normal distribution. So the mean actually increased by 1/2 of one standard deviation with a sample size of 50 purely by one outlier, the presence of one outlier. On the other hand, with a sample size of 500, the mean increased by 0.03 standard deviations. So that's a pretty remarkable change. Okay, and then the median doesn't change at all. And why doesn't the median change at all? The median doesn't change at all because it's a nonlinear measure of a distribution centrality. So the total number of data points to the left and to the right of the center of the distribution are exactly the same. So therefore, the median is not impacted by this outlier the way that we created this. Now, it doesn't mean that the median cannot be impacted by an outlier. For example, here, let's say we ran the simulation differently. Instead of replacing the largest data value by itself to the power of 4, what if we just picked a random data value and replaced that by the number 1 billion? So, that number that we picked randomly could have been negative, which would have meant left of the median, and then it becomes right of the median. So that actually would have impacted the median by at least a little bit. The last thing I want to mention in this video is just a comment about these distributions. So this histogram here looks beautiful. It looks really great. N of 5,000 is going to give you a really nice, clean distribution of data where it's so visually obvious that these data are drawn from a Gaussian distribution. Here, however, it's a little bit more ambiguous, right? So this sample size, n equals 50 it's not big, but it's not tiny. I mean, this is not a really small sample size. Many, many research experiments with sample sizes of 20 or 30. And here we look at the histogram. And I mentioned earlier in this video, it kind of looks like it's bimodally distributed, but it's really not. This is just due to pure chance that we end up with no or very few values, just one value in between these two bounds. So when you have a large sample size, you can be more confident in interpreting the visual features of a histogram. When you have a small sample size, then it's just harder to make confident evaluations of a distribution characteristic purely based on visual inspection of the graph. Here we are with exercise 7 of chapter 4. Now, you can compute the statistical moments of data using formulas that I introduce in this book chapter, but you can also compute the statistical moments of analytic functions using the SciPy.Stats library. And that is what I will introduce you to here in this exercise. So in the SciPy.Stats library, and then .norm.stats. So the .stats is going to return the statistical moments, or in general, it returns features, properties, characteristics of the normal distribution. Here I'm specifying the location, which is the mean, the scale, which is the standard deviation, And then this optional parameter here, moments, and I write mvsk. What does mvsk stand for? So mvsk is not actually one individual word. It is 4 separate letters. And this is telling Python that we want to compute the mean, the variance, the skew, and the kurtosis. So that's what these first letters stand for. Mean, variance, skew, and kurtosis. And that is going to be the outputs of this function. So what I am going to show you is basically just extracting these 4 properties, these statistical moments from a normal distribution, and then we're going to change these values to see how that relates. And notice that, we're not using any data here. So these are analytic results from a formula. And then, well, I'm not going to do this in the video, but I encourage you to start exploring this for other kinds of functions, other analytic distributions. And this is just kind of general knowledge. This is not something that I use a lot in this book because, this book is really all about applied empirical statistics. If you are interested in more kind of mathematical statistics, then you are going to be using, you would probably use a function like this fairly often. So yeah, the code is really straightforward. It's exactly what I just showed. Okay, so we can run this code. We see that the average value is the first moment, that's 4. The variance is, 1. The variance is the second moment, that's 4. And what is this? Shouldn't it have been 2? Well, the scale parameter actually corresponds to the standard deviation, and the relationship between standard deviation, or what Python here calls scale, and variance, of course, as you know, is just a squaring. So whatever you put in here, the variance should be that number squared. Okay, and then we have skewness and kurtosis. This is the normalized kurtosis, or excess kurtosis, it's sometimes called. These are both equal to 0, and that is not surprising because this is a normal distribution. Normal distribution is perfectly symmetric. It's a Gaussian, so there is no skew, and there is no excess kurtosis. Okay, so that's basically all I'm going to do in this video. I certainly encourage you to spend a few moments to play around. You can change these parameters, see how that impacts these results. You can try uniform distribution, like normal distribution, exponential normal distribution. There's lots of distributions you can try by going to this website. This is just for your fun and educational experience. I encourage you to just play around and see what you can discover. Statistical moments of a distribution or of a data set are important because those are numbers that provide insights into the characteristics of the data. Of course, you know that the mean, which is the first moment of a data set, is like the most common thing to evaluate in statistics, right? T-tests and ANOVAs are all about testing means, which is just the first moment of a data set. But there's also other moments. There's the second moment, which is variance, the third moment, skew, the fourth moment, kurtosis. These are not as frequently quantified and statistically compared across data sets as compared with the first moment, the mean, but they are. So kurtosis, for example, is used all the time in signal processing. For example, independent components analysis uses estimates of kurtosis to identify components in the data. Financial risk assessment often uses kurtosis as a measure of risk in investment profiles and so on. Okay, so anyway, here we are in exercise 8. We are going to explore how the first 4 statistical moments are impacted by changing the distribution. And in particular, we are going to focus on a exponential distribution. So what you want to do is write a Python function that computes the first 4 statistical moments of a data set that you input. If you want a little bit of an extra challenge, you can write out the formulas for mean, variance, skew, and kurtosis on your own, but don't worry about that. It's really not necessary for this exercise. Instead, what I have done, what I encourage you to do, is use the functions in scipy.stats to compute mean, variance, skew, and kurtosis. Okay, so then create one data set. It's just one data set with 13,524 numbers drawn randomly from a standard normal distribution. And then from here, you transform these into another data set that is e to the x sigma, where x is these numbers that you have randomly drawn, and sigma is a scaling parameter that varies from 0.1 to 1.2 in 20 linear steps. And then here I write that basically what you want to do is create all these different data sets as scaled versions of the same variable x. So each of these 20 different data sets, they do not come from a unique sampling of 13,000 numbers. Instead, you sample 13,000 numbers once, and then you transform those numbers repeatedly by varying sigma. So x is always the same in all of these steps. I think that's just interesting. It makes it a little bit cleaner to interpret the results. Okay, here you see some different distributions for different values of sigma. When sigma is very small, then the distribution looks very Gaussian, it looks very normal. And the larger sigma is, the more you are stretching out these numbers here, so you get larger and larger values of x, and that is going to pull the distribution to the right. And it has to pull this distribution to the right because e to the something is a positive valued only function. It cannot be negative. Even when x is negative, when values of x are negative, e to the x is a very small positive number. So that means that this distribution ends up getting shifted to the right. It pulls to the right. So of course that's going to impact the skew and in particular the kurtosis. And that's what you see here. So these are the values of sigma, and there's 4 dark gray lines here, or grayscale lines here, corresponding to the 4 different statistical moments. And you can see that the mean and the variance and the skew are a little bit impacted, but really strongly impacted is the kurtosis. This is just absolutely blowing up. And that's not so surprising because we are raising these values to larger and larger, or I should say we are scaling these numerical values larger and larger, which means e to the something is getting larger. And then we take that to the 4th power to get kurtosis, so that value is just going through the roof. Okay, I'm going to say a few things. I have a few comments I'd like to make, a few observations about these results, but I will make that in the Python code when I produce this graph. So here is the Python function that computes and returns the statistical moments of a data set. It's not exactly the same thing we were doing in the previous exercise where we were computing the moments of analytic distributions. These are empirical moments. So you can see I'm using NumPy for mean and variance, and then here I use stats.skew and stats.kurtosis. Very simple, very straightforward to use. Okay, and then I just return them all. Let me run that cell. Here is where I create all of the data sets. So let's see, these here I'm defining the sigma parameters. Here is the variable x of 13,524 standard normal numbers randomly drawn from a standard normal distribution. And then here you can see I'm creating the data, and as I showed in the book, so it's e to the x times sigma, and then I'm just storing all 4 of those moments, calling this function moments. So that's all going into this matrix results M. So it's the length of sigmas by 4 because we have 4 moments that we are computing and storing. So run that code. That's very fast to run. And then here's some plotting. The plotting, this code gets a little bit hairy here because of all the things I'm doing, in particular the annotate function. I'm not going to go through each of these lines of code here in this video, although I do encourage you to go through them as well. It just, basically just create. Most of the stuff I think is really easy and straightforward. Maybe drawing these arrows is a little trickier, but anyway. So it does kind of look like these first 3 moments are hardly affected at all, but to some extent this is just a scaling effect because the kurtosis, because these are data values raised to the power of 4, it gets really large really fast. And so to appreciate that these first 3 statistical moments are also varying, as a function of the sigma parameter, we can uncomment this line here, which logarithmically scales the y-axis here. And then you see that, all of these parameters really are changing as a function of the change in the shape of this distribution. So this is pretty interesting to see because, we often get stuck in this old school traditional idea that the only interesting feature of a data set is the mean, right? As I mentioned in the beginning of this video, we use the mean most of the time in inferential statistics. For t-tests and ANOVAs in particular, we really just care about the mean. And even for other analyses like correlation and regression, those are essentially just analyses based on the second statistical moment, which is variances and covariances between different variables. It's relatively infrequent that we are actually specifically quantifying and comparing higher statistical moments in inferential statistics. And I think a lot of that is just historical. People are just typically interested in the mean and not in anything else. But you can see that these other distribution characteristics can be really informative. In this particular case, the kurtosis is the most striking indicator of the shape of this distribution, much more so than the mean, which is barely changing as a function of the really huge qualitative changes in the shape of these different distributions. Here we are with exercise 9 of chapter 4. I hope you enjoy these exercises. I know some of them are a little bit long, some of them are a bit involved and take some time to complete. But, I find these exercises that are very short and easy to do to be pretty boring, to be honest. So I tried to design my exercises to be a little bit more involved, a little bit more like projects than, sort of typical textbook exercises. And anyway, I hope you find these insightful and useful. Okay, that was just a meta comment. It has nothing to do with this exercise. This exercise is about the relationship between IQR and standard deviation. So, interquartile range and standard deviation are conceptually similar. They both measure the spread of the data in a distribution. But IQR is a nonlinear measure. It's all based on medians. So it's not the same thing as a standard deviation. On the other hand, you know that the mean and the median are basically either exactly the same or really, really close to being the same number for standard normal distributions, or in general, any symmetric distribution. So in fact, it turns out that not only are the mean and median similar for a normal distribution, but the IQR and the standard deviation are closely related using by this scalar. So basically, the IQR is around 1 1/3 or 1.35 times the standard deviation. This is not trivially always the case. That is just true for a perfect normal distribution. So the first part of this exercise, there's two parts of this exercise. The first part is to confirm that this is approximately true. We don't need to, it doesn't need to be exactly 1.35, but approximately by generating 10,000 random numbers generated from a normal distribution. So generate 10,000 standard random numbers and show a histogram like this. And then you can plot the quartiles around the median and the standard deviation divided by 1.35 around the mean. Here, this says 1.5, but that's a mistake in the code for the book, which I've already fixed. So by the time you see the book, it's going to say 1.35. So anyway, so you should see the standard deviation, scaled standard deviation, and the IQR is not going to be identical, but they should be pretty close to each other. So that you can see here. And the second part for this exercise is to basically run exactly the same code, but using non-normally distributed data. And here you are going to basically push these numbers through the natural exponential function, which transforms the normal distribution into a log normal distribution. So this is data set X, and then this is data set e to the x. And then I have a few observations and comments about this, but I will talk about that when I show the Python code. So here I create the normal distribution of data. Here is exactly the same data, but then pushed through the natural exponential function. I call that variable EX. Here is the interquartile range and the standard deviation for the standard normal distribution and the log normal distribution. You can see I'm using this DDoF parameter of 1 in both of these cases. Okay, and then here I'm reporting them. And well, you see that for the normal distribution, they are almost identical, really, really, really close to each other. And for the log normal distribution, they are not even close. I mean, this one is like twice this one. Okay, and then here I'm plotting the data. So yeah, this is pretty straightforward. Just computing the mean and the standard deviation. Here I'm dividing by 1.3, so that's doing the scaling, and then showing the histogram and making the plot. So that looks like this. Okay, here you see the plot. So this looks like, what I showed in the book figure. And now a couple of points I would like to make. First of all, for a standard normal distribution, you can see that the standard deviation and the IQR, the different quartiles, are not identical, but really, really close. And they're also equidistant from the center of the distribution, which is either the mean or the median for these two different metrics. And yeah, you can see either one of these is a useful representation of the amount of spread in the data on both sides, because the distribution is not going to be exactly perfectly symmetric because of random numbers, but it's roughly symmetric. Here, on the other hand, this is the more interesting case because, yeah, some of these, I mean, this is just weird to have one standard deviation, not even a standard deviation. It's scaled, 0.8, whatever, standard deviation below the mean. And that's basically at the lower boundary, right? There isn't really any data below this dotted line, this dashed line over here. And that is, if you interpret a standard deviation in the way you think of interpreting a standard deviation, then this doesn't make sense, right? There's almost no data below one standard deviation. And the problem here is that the standard deviation is harder to interpret. Numerically, it's fine. Mathematically, we can still compute it. But the interpretation becomes difficult because this is a non-normal distribution, and quantities like the standard deviation are really only easily interpretable for a symmetric and ideally Gaussian distribution. So the quartiles, on the other hand, which are used to define the interquartile range, are much more conducive to interpretation in this non-normal distribution. And that's because basically what this line tells us, this black line, tells us that 25% of the data are to the left of this line, 25% of the data are to the right of this line, and 50% of the data are in between those two lines. And that is a much cleaner and more accurate interpretation of these distribution metrics. The goal of exercise 10 in chapter 4 is to develop an algorithm or write an algorithm that will compute the full width at half maximum of a Gaussian distribution. Now, to do this, we need to validate this algorithm, and we are going to validate the algorithm on a pure Gaussian, so an analytic Gaussian, where we can compare the results to the analytic full width at half maximum. So there's a couple of points here, 6 points, but I'm actually going to scroll up to a figure in the book to illustrate what these points actually mean. So this is figure 17 of this chapter, and here I draw a Gaussian function. So here is how you compute the full width at half maximum. First of all, you need to normalize the Gaussian so that it has a peak of exactly 1, and it tapers down to 0. So the smallest number should be 0, and the largest number in the Gaussian should be 1. This is illustrating 100%, but scale it to 100 if that makes you feel better. Okay, and then you want to identify the points to the left and to the right of the peak that correspond to the value of 0.5. And again, here I'm showing 50%, but that's just because it's scaled. So 50%. So this is the half maximum. That's the HM part, half maximum. And then you want the full width. And so the full width is the distance on the x-axis that goes from this point here until this point here. So the full width at half maximum of this particular Gaussian is, you can see it's the number 4.47, but you can think of it as being, it's this distance here. So it's from here to here, and you can see visually, so this is -2 to +2, so that's 4, and then it's a little bit higher than that. So it ends up being 4.47. Now, if you have an analytic Gaussian, if you're creating a Gaussian function by a formula, then you can actually just use this equation here to get the full width at half maximum of this Gaussian. So it's 2 sigma times the square root of 2 times the natural log of 2. And this basically just falls out of working with this formula. By the way, you can see here I've dropped the amplitude scaling term that you have seen before with the Gaussian. We've played with that in previous exercises. The reason why you don't need that here, you don't even want that here, is because you want this function to have a value of 1. So the function value is 1 when x equals 0. And you can see that that's going to be the case here, because when x equals 0, then you have 0 over something. It doesn't matter what sigma is. This is going to be 0. So then we have e to the 0. Anything to the power of 0 is 1. So then the value of this function, g of x, when x equals 0 is 1. And that will facilitate the empirical computation. So to start with this exercise, I know that was a long explanation, but to start with this exercise, compute the full width at half maximum and compare it to, compare this formula to the algorithm that you are going to write. If you get completely wildly different results, like you get an empirical full width at half maximum of, 104, then something is wrong with your algorithm. You should get something extremely close to this number. Maybe not identical, depending on how finely you cut up this x-axis grid here. So here I say if you use parameters of sigma equals 1.9 and the x-axis goes from -8 to +8 in 1,001 steps, you should get exactly these numbers. You should be able to reproduce this result. Okay, so then test your function on a range of sigma parameters from 0.1 to 5 and plot them. So you see that the analytic and the empirical full width at half maximum calculations are the same up until, like around 3 or a little bit above sigma equals 3. And then they start to diverge. So you have to figure out what is the problem here. Why are they diverging? Of course, I'm going to tell you the answer. So there's more to do in this exercise, but I think I'll switch to code and walk through this, and then I'll come back to the rest of this exercise. Conceptually, I believe that this algorithm makes sense when I walked you through the algorithm steps in with the figure. So here we normalize to a range of 0 to 1. This should look familiar from the chapter on data transformations. This is min-max scaling. And then we find the location of the peak. And the only I think this part is also pretty easy. The only challenging part of this algorithm is figuring out this part with the value after the peak. And there's this just kind of weird housekeeping thing where you subtract 1 from the index. And basically the reason why you have to do that is, or to understand why you need to do that, think about what would happen if the value at 0.5 was exactly at the peak. And then I think that will give you some insight into why this indexing needs to be the way it is. Okay. So then this function, I'm going to return the full width at half maximum, which is the distance between the 0.5 values pre and post the peak, and then the actual index values here, or the x-axis values, sorry, not the index values. Okay, so then here we are comparing it against the analytic function. Here is I'm just creating a Gaussian. And here, this is the analytic full width at half maximum. I showed you the formula in the book. And this is just to make sure that we get almost exactly the same result. Of course, it's going to be off a tiny bit just because of discretization. You can actually change this value. You can get the match to be closer or further away depending on this resolution here, if you're curious to play around with that. Okay, so now we are going to test this across a range of values. And here is where we got this discrepancy here. So what's going on here? So it turns out that the problem is that the later Gaussians don't have a wide enough x-axis range. So let me show you this figure so you can see what this looks like. Now, remember that part of this algorithm involves scaling the Gaussian function so that the smallest value is 0. Now here, when you see this original Gaussian, you can see that basically the sigma parameter is so large relative to the range of x-axis values that we're not actually getting this function down close to 0. So in fact, the function is only going to like 2.8 or whatever. And yet we are artificially scaling this down. So after normalizing this function, so it goes from 0 to 1, it actually ends up artificially shrinking or compressing this Gaussian, which is really wrong. It's inappropriate. So, but this is, part of this exercise was to make you aware of these kinds of issues. Again, this is, a theme that comes up very often in this book and also in my teaching of applied math in general. There are often discrepancies between pure math and computer math, and this is one of these areas where there's something that you need to worry about in when implementing mathematics in computers. And on a chalkboard or on a piece of paper with a pen, you don't worry about this stuff because you think about the x-axis as being, sort of infinitesimally discretizable and going from minus infinity to plus infinity. Okay, anyway, the point of that is we can solve this issue by just having this x-axis range be larger. So I'll make this, let's just say minus 18 to plus 18. It's probably maybe a little too much, but let's see. Now we find a really great match. Again, we could push this further. So eventually, you can increase the top value of sigma and eventually get to a point where this is going to be mismatched as well. So here, I'll run this as well. And you see that the original and normalized are now basically identical. You have to look really, really close to see that there's even a tiny discrepancy. So that part of the exercise was about developing and validating this algorithm to compute the empirical full width at half maximum. Now what I want to do is apply this to a distribution of real data. So we're not generating a Gaussian function anymore. Instead, we are randomly sampling data from a normal distribution. So we sample 1, 2, 3, 4, 5 data points randomly sampled from a standard normal distribution, generate a histogram using 100 bins, and compute the empirical full width at half maximum using this algorithm that you just defined. So there's some comments that I'd like to make about this, but I will make that when I show the Python code. Now, there's nothing anymore new. There's no new code in for the rest of this exercise. Generate some random numbers, get the histogram, and compute the empirical full width at half maximum on the data from the histogram. Okay, and then make a visualization of this. Okay, now, so, what do you think about this? I find these plots to be really interesting. I have, in my own research and in the research in my lab, we have used this metric, so empirical full width at half maximum. One issue is that you need a lot of data to trust this measure, and that's because you want this histogram to be really well sampled. The issue is that, let's say you have only 20 bins. Actually, maybe I'll just do that. Okay. Let's say 20 bins. So actually still looks okay because we have so much data. Okay, let me try again. I'll get rid of one of these things. So now we have only 1,200 data points, which is still a lot. Okay, but here, now we're starting to see, I'm going to make this even more extreme. Let's just say 100 data points. 123 data points is not that small. Okay, but now maybe 20 bins is too much. Let's try, how about 14 bins? So this looks weird, to say the least. One thing, the way that I've drawn this plot is to empirically draw the height according to half of the distance, and it's not actually connecting the peaks, but it's going to be basically this line here to this point here to this point here. So it's totally, there's just no way we can try rerunning this. It looks really horrible. But the point is, okay, this is slightly better because this distribution happened to look a little bit more Gaussian. But I think you are clearly seeing the issue here, which is that this empirical estimate of the full width at half maximum doesn't really work very well for small sample sizes. It doesn't work very well for histograms without a lot of bins. So this is not something you would just apply to any random data set without thinking carefully about whether it's appropriate. So let me set these numbers back. And now if you have a large amount of data and a sufficient number of bins, then I do think that this can be a valid and potentially insightful measure of the width of the distribution. But yeah, you just want to be mindful about uh, when you are applying this and how you are interpreting this. Exercise 11 of chapter 4 is focused on histograms and visually interpreting histograms when you use different numbers of bins to generate those histograms. Now, you can see an example here. These are exactly the same data. So not changing the data between these 4 different lines. What I am changing is the rule for how to generate the number of bins. So here in blue, I just arbitrarily picked the number 40. Here's the Friedman-Diaconis rule, Sturgis's rule, and Scott's rule in red. Now, Scott's rule, I didn't actually define specifically in this book. I do mention it here. It's basically just, based on standard deviation and sample size. Now, what you see is that some of these histograms are taller or wider than others. And really what's happening is that when there are fewer bins, there's more data that goes into each bin. So therefore, the count is higher. So there's, you can normalize this. I'll talk about this in the code. But this means, this has some important implications for interpreting distributions, because it basically means that you should never really interpret the small scale features of a distribution. Like this here, I mean, this really does go down, but is that a meaningful decrease? Here, you don't see a dip in any of these other distributions here, even though it's exactly the same data. So, whenever you look at a histogram, unless you have a ginormous amount of data, like millions and millions of data points, you really should be like squinting, sort of low pass filtering these histograms and not over interpreting them. Okay, so now let's switch to code. We'll generate a distribution. Let's see, this comes from just 1,000 numbers drawn from a random distribution. And then, we'll try some other distributions once we look at the code and talk about this in a little more detail. The code is pretty straightforward. We just generate some random data here. And then in a for loop, I am going to use these different bin options, so different rules or guidelines for how to choose the number of bins. So otherwise, the code is pretty straightforward. Use numpy.histogram and then just plot. Okay, and then, this just looks like what I showed you in the book. Now, one thing, there's a couple of things I want to show you. One is using a bar plot. Now, you might think that we should be using a bar plot because, again, the issue is we don't really know what is the distribution of data between this point and this point, or, the center of this bin and the center of this bin. Arguably, we should not be using lines here between these points. Now, then, actually, let me start by showing you this. Just the same thing, but getting rid of the lines. In my opinion, this is harder to look at. This looks like one of these old school 1990s visualizations of music on an MP3 player or something like that. Like, it looks pretty neat, but I don't find this to be as visually interpretable as if there are lines there. And maybe, I've discussed this before, but a purist statistician might say, or a purist data visualizer might say, you can't really show any lines here. You have to show bars. And that's fine. We can do bars. The problem is, the bars start overlapping and they get to be impossible to interpret. So, we could play around with this. If you would like to do that, then go for it. You can play around with this, change the parameters of this bar plot to get it to, be able to visualize all 4 of these bars. In my opinion, just sometimes you got to break the rules to facilitate visualization. Okay, there's another thing we could do. which is to normalize all of these. Oh, look at this with Scott's rule. This looks really beautiful, nice and round and symmetric. We could normalize these so that instead of having count, we are doing proportion relative to the maximum. So I'm going to just divide y by the max value of y. And now we are normalizing the distributions so that they all have a maximum value of 1. And this is pretty interesting because now you see that these distributions actually look more similar to each other when they are normalized, right? So it appears that the widths are all the same as well, right? So here I'm just running it again just to generate new random data. So here we really see that these distributions look really, really similar to each other when they are normalized. And that I think is striking because if we go back here to the non-normalized results, it looks like this green distribution is wider than this orange distribution. It's not really wider. It's that the entire thing is scaled up. It's scaled up on the x-axis, and so it's also scaled up on the y-axis. I think the important take-home message from this exercise, as I mentioned before I switched to Python, is looking at histograms is really great. I strongly encourage you to visualize your data in many different ways, and histograms are a great way to visualize and to understand the characteristics of your data. But don't overinterpret histograms and try plotting them with lots of different rules for the number of bins. Okay, the last thing I want to do here is just see how this looks with a uniform distribution instead of a normal distribution. So it looks like the orange line is dropped out. And what's actually happening is that this orange line just overlaps perfectly with probably Sturgis's rule. I think these two might be similar to each other. But anyway, now you have this code. I encourage you to continue exploring this with different distributions, different sample sizes, and so on.